Go ahead and get started. Most of this, at least 9.1, is a lot of fill in the blank. There's not a lot going on in here. So we're trying to get through half of it today, and then, sorry, and then the rest of it tomorrow. All right, so your introduction, we talked about confidence intervals in chapter 8. So confidence intervals are one of the two most common types of statistical inference. We use a confidence interval when your goal is to estimate a population proportion, or any parameter for that matter. It could be a mean as well. The second common type of inference called significance test. Has a different goal, and it's to assess the evidence provided by data about some claim concerning a parameter. Right, so you guys can go back and read that activity and check out the applet or whatever, but it's talking about a free throw shooter shooting shots. So in the free throw shooter activity, the parameter of interest that we were looking for was the probability P of the free throws that the player will make if he shoots forever. Our player claims that he can shoot 80%. So to test his claim, we let the applet simulate 25 shots. If the player makes only 40% of his free throws, which would be 10 out of 25, we have fairly strong evidence that he doesn't shoot 80%. But what if he makes 76% of his free throws? So that would be 19 out of 25. This provides some evidence that his true long-term percent may be less than 80, that it's not nearly as convincing as that sample proportion of 40%. Statistical tests weigh the evidence against a claim, and we'll talk about that when we get there. Like our P equals 80%, and in favor of a counterclaim like P is less than 80%. Okay, sounds weird right now, but it's actually not as bad as it sounds. Section 9.1 focuses on the underlying logic of statistical tests. Once the foundation is laid, we consider the implications of using these tests to make decisions about everything from free throw shooting to the effectiveness of a new drug. So in section 9.2, we'll present the details of performing a test about a population proportion. And in section 9.3 shows how to test a claim about a a population mean. So proportions in 9.2 and means in 9.3. Along the way, we'll examine connections between confidence intervals and test. All right, so just like last chapter, we'll do proportions first and then we'll do means after that. So 9.1 is just introducing you how to write everything, okay? This is how you write it. 9.1 focuses on that state plan do conclude again, where you're doing everything, but it's only for proportions. And then in 9.3, it's all about means. So kind of the same way that 8 is set up. So I left the blanks in the top of this one. So these are the things that you need to know at the end of 9.1, which will be at the end of the day tomorrow. You're going to be able to state the null and the alternate. I say alternative sometimes. Hypothesis is either or. For a significance test, about a population parameter. So you are going to come up with the two hypotheses. Really simple, really simple. You're going to be able to interpret a p-value in context. So that's the same thing as like interpreting the mean, interpreting the standard deviation. You'll have the same sentence. You just change it with whatever your p-value is in your context. So it's the same thing over and over and over again. You're going to determine whether the results of a study are statistically significant. And I screw that up every time. Statistically significant. And make an appropriate conclusion. Using a significance level. So bullets 2 and 3 we will do tomorrow. 1 and 2 we're going to do today. 2 and 3 we'll do tomorrow. You're going to be able to interpret a type 1 and type 2 error in context and give a consequence of each. Those are the ones that are like everything else. I feel like it's pretty easy to memorize. The last ones are the ones that you'll get mixed up. So just be careful when we start doing those that you understand what they are. But again, the last 2 bullets we're not doing until tomorrow. Okay. So a significance test is a formal procedure for using observed data to decide between 2 competing claims, also called hypotheses. These claims are often statements about a parameter, like the population proportion P or the population mean mu. So let's start by taking a closer look at how to state hypotheses. All right. significance test. Starts with a careful statement of claims. That we want to compare. In our free throw shooter example, the virtual player claims that his long run probability of made free throws is 80%. This is the claim, because that's what he claims, that we seek evidence against. We call it the null hypothesis. And that's abbreviated H sub O. Null is 0, so H sub 0. Usually the null hypothesis is a statement of no difference. So there's no difference in that null hypothesis compared to the claim is what it's going to be. So for the free throw shooter, no difference from what he claims gives, and this is exactly how you write it, H sub O and a colon, P equals 0.80. That is one of your two. That's your null hypothesis. Okay. The claim we hope or suspect to be true instead of the null hypothesis is called the alternative.
So is the difference the null one you want to be wrong? Like
yeah, we're trying to prove that it's wrong.
And then the next one is
They'll tell you, yeah, and they'll tell you exactly what it is. So if we're talking about an 80% free throw shooter, we're probably going to test the claim that it's less than. Okay, 80% is really, really good. So we think he's not very good, but it'll tell you. It'll tell you what to do. All right. We abbreviate the alternative hypothesis I do H sub A. You might see it as alpha. It doesn't matter which one you put. They don't care. Okay. I like H sub A, so you'll keep seeing that. In this case, we believe that the player might be exaggerating. So our alternative is H sub A, P is less than 0.80. So we don't think he's that good. Okay. And again, it'll tell you in the problem, and we're going to have examples of it in just a minute. So it's not a big deal. Okay. So just to summarize what we did, the null hypothesis is H sub O. The alternative is H sub A. The claim we weigh evidence against in a statistical test is called the null hypothesis. Which is H sub O. Often the null is a statement of no difference. The claim about the population that we are trying to find evidence for is the alternative hypothesis, or H sub A. All right. So when we flip it over, it's just going to summarize it one more time and exactly how you should write it. So in the free throw shooter example, our hypotheses are, and you'll write them just like this. H sub O is P equals 0.80. And H sub A is that it's less than 80. Where P is the longer run probability, of made free throws. The alternative hypothesis, that's the P is less than 0.80, is one-sided because we are interested only in whether the player is overstating his free throw shooting ability. Okay, so let me explain this one-sided and two-sided to you because it will make a difference. Okay, it will make a difference. So if we have less than, it's just going to be over here on the left side. It's only on one side. That's why it's called one-sided, like honestly. If it's to the right, it would be on this side. So it'd only be on one side of that line. If it's two-sided, it's going to be like this where it's not equal to, and you'll see that soon. Okay. So the difference between one-sided and two-sided. And when we do it in our calculator, you're going to have to know the difference between one-sided and two-sided. Is it the left side? Is it the right side? Or is it two-sided? Okay. So because H sub A expresses the effect that we hope to find evidence for, it is sometimes easier to begin by stating the alternative and then set up the null. It is however you want to do it. It doesn't matter. As the statement for the hope for effect is not present. Here's an example in which the alternate hypothesis is two-sided. All right, so just going over this one more time. If it's one-sided, it's either less than or greater than. Okay.
What does it mean we're trying to find evidence for it?
We'll see that. Right now, when we get to like 9.2, you're going to see that a little bit better. Let's just work on writing the hypotheses, and then it'll show you exactly what you're doing. When you state, actually, you'll probably know it in just a minute when you state conclusions. So just give it a minute, and it'll make more sense when you see an example than if I try to explain it right now. Okay. And then a two-sided is going to be not equal to. So it's going to be on one side of it or the other, not equal to it. All right. So it says at the Hawaii Pineapple Company, managers are interested in the size of the pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in this field after the growing season. Managers wonder how this change will affect the mean weight of pineapples grown in the field this year. So if it is one-sided, it will say something like, managers feel like this is less than it was the previous years. Got it? Or they'll say, if it's other side, think that they have grown larger. Got it? This one doesn't say either side. It doesn't say less than or equal to. It just says they changed. So if it just says they changed, that's going to be a not equal to. So when it says state appropriate hypotheses for performing a significance test, be sure to define the parameter of interest. So we're going to start with our null, which is no difference. We're talking about the mean weight. So mu, sorry, these should be a colon, is going to equal 31. There was no change at all. So what were they? They were 31. Again, it says define the parameter. Mu is the mean weight of pineapples in the field after the growing season. Okay, I would be as specific as possible when you're doing your final exam. I don't care right now. Your alternate is going to be that the mean does not equal 31. Why does it not equal 31? It doesn't give you a specific side. So it could be less than 31 or greater than 31. So we just say that it's not equal to it. Okay, so those are the weird ones. That makes it two-sided. You're going to do this again in a page and a half. Okay. So we're going to see more examples of this. So if you're not understanding where they came from, we're going to do more. After the check your understanding, if you don't understand, then you need to talk to me and we need to figure it out. Okay. So the hypothesis should express the hopes or suspicions that we have before we see the data. It's cheating to look at the data first and then frame hypotheses to fit what the data show. For example, the data for the pineapple study showed that the sample mean was 31.935 for a random sample of 50 pineapples grown in the field this year. You should not go back. You should not change the alternate or alternative hypothesis to mu is greater than 31 after looking at the data. If you do not have a specific direction, like we did not have one, then we should always use a two-sided alternative hypothesis. All right. So the definition of a one-sided and a two-sided, and I already showed you what that was, but this is going to go into a more formal definition. A one-sided, if it states that a parameter is larger than the null hypothesis value, or if it states that the parameter is smaller than the null value. So that's one-sided. It's either less than or it's greater than. It is two-sided if it states that the parameter is different from the null. So then it could be either larger or smaller. But again, it will state it specifically. And when we get to the check your understanding in just a second, you'll see it. So the null hypothesis has the form H sub O, your parameter, whether it's mean or proportion, mu or the p, equal to the value. It is always equal to the value.
Wait, is this supposed to be a semicolon or a colon? Doesn't matter.
It's a colon. It's okay. The alternative hypothesis has one of the forms. H of A, the parameter is less than the value. H of A, the parameter is greater than the value, or the parameter is not equal to the value. So it's going to be one of those three. To determine the correct form of your alternate, read the problem carefully and stay on this page after I finish this. Hypotheses always refer to a population and not a sample. So it's always going to be mu or p, not p hat, not x bar. That's all it's telling you. We're not doing this. That's exactly what I was just saying, so it's not important. So be sure to state your null and your alternative hypothesis in terms of the population parameters. It is never, you'll get counted off for this. It'll automatically stop grading your paper. It is never correct to write a hypothesis about a sample statistic such as p hat equals 0.64 or x bar is greater than 85. So those deal with samples and we're talking about population. We're doing a page and a half. So front and back of the next page and then the front of the next one and we'll be done. Okay. Give me just a second. All right. So check your understanding. We're going to be describing the parameter of interest. So just define it and then state appropriate hypotheses for a significance test. So according to the website sleepdeprivation.com, 85% of teens are getting less than 8 hours of sleep at night. Janie wonders whether this result holds in her large high school. She asked an SRS of 100 students at the school how much sleep they are or they get on a typical night. In all, 75 of the responders said less than 8 hours. So we're going to start with that one. The first thing we're going to do is define our parameter. Our parameter is going to be P because it's a proportion, 85%. It is the proportion, I don't know why I put a dot there, of all students in her high school who get less than 8 hours of sleep at night. Yes, you need to be that specific, okay? Where did that come from? Right here, okay? Teens are getting less than 8 hours of sleep at night, and she's wondering about her high school, okay? So then what's our null hypothesis? It's the one that we know or that will not change. What is the proportion that it gave us? 85. Does it say that they get more or less or what? Okay, that's what our thing tells us, right? That's the data tells us. So we can't base our prediction on that. What does it say? She wonders whether this holds true 85%. Does it say she wonders if it's less than that or she wonders if it's greater than that? No, it said it was less than, right? That is a result. This is a result, and we can't base our stuff off of that result. So all we want to know on this one is if it's different than 85. Just that it's different. Now, what's going to happen is we're going to get a long thing where we have to figure out, okay, this is our result. Here's our result. Now, what can we say? Okay, can we come to a conclusion? Does that make sense? So we'll use that result later on, but we can't use it to make our hypothesis. So 2 is a little bit easier because it's not a two-sided. Okay. As part of its 2010 census marketing campaign, the U.S. Census Bureau advertised 10 questions, 10 minutes. That's all it takes. On the census form itself, we read the U.S. Census Bureau estimate that for the average household, this form will take about 10 minutes to complete, including the time for reviewing the instructions and answers. We suspect that the actual time it takes to complete the form may be longer than advertised. So here's the difference. This is a result. This is what we're trying to predict. Okay. So what is our parameter? Do we have a proportion this time? What do we have? It is the mean, so we're doing mu. And what is it? What is it in context of the problem?
The time it takes for a household to finish the survey, the
Okay.
10 questions.
And make sure that you write the word mean in there somewhere. So we write true mean amount of time. It takes to complete the census. Very good. And again, you could say for the average household. Right. So what did they tell us that it would take? So our mu would equal 10. We suspect that it would do what?
Take more than
Longer. So what are we going to put here? Greater than 10. Perfect. Make sure you know your difference between your greater than and less than sign. It's super important. Okay. That's it. That's how you write a hypothesis. So if it doesn't state a side, we suspect it's longer, we suspect it's shorter, then make sure that you make it a two-sided like we did in this one. Okay. Back page and front page and we're done. Significance test. Ooh. I have a weird page here. Hold on, it's really weird. Give me just a second. I think it ate the pages wrong. Let me make sure we're going in order, okay? Sorry, y'all. This is right. I'll do it this way. Sorry. Maybe I'm missing pages in this one. This page is right. My packet is wrong. No worries. All right, significance test. Ask if sample data give convincing evidence against the null hypothesis, and in favor of the alternative. A test answers the question, how likely is it to get a result like this just by chance when the null hypothesis is true? The answer comes in the form of a probability. Here's an activity that introduces the underlying logic of significance tests. So the activity is a great free throw shooter. I'll go ahead and read it since I have my book open. Our virtual basketball player in the previous activity claimed to be an 80% free throw shooter. Suppose he shoots 50 free throws and makes 32 of them. His sample proportion of shots made is 32 over 50 or 64%. This result suggests that he may really make less than 80% of his free throws in the long run, but do we have convincing evidence that the probability is less than 80? In this activity, you and your classmates will perform a simulation to find out. So we would simulate all of this, okay? Moving on. Our reasoning in the activity is based on asking what would happen if the player's claim, so he claimed 80%, just like before, were true, and we observed many samples of 50 free throws. We used the Fathom software to simulate 400 sets of 50 shots, assuming that the player is really an 80% shooter. The following figure shows a dot plot of the results. So there's all 400 of the samples. Each dot on the graph represents the proportion of made shots in one set of 50 attempts. For example, if the player makes 43 of 50, the dot would be placed at p hat equals 0.86. You can say how strong the evidence against a player's claim is given is by giving the probability that he would make as few as 32 out of 50 free throws if he really makes 80%. In the long run. So based on the simulation, our estimate of this probability is 3 out of 400. Which is equal to 0.0075. The observed statistic, which is p hat equals 0.64, is so unlikely if the actual parameter value is 80. Sorry, this should say actual. Sorry. P equals 0.80 actual parameter value. That gives convincing evidence. Let's see, convincing. It should just say evidence. No, I am screwing up everything today. That the player's claim is not true. Okay. So going back over that, you can say how strong the evidence against the player's claim is by giving the probability that he would make as few as 32 out of 50 free throws if he really makes 80% in the long run. Based on the simulation or estimate of this probability, so if you guys can look at it, here's 64%. Only 3 of those are less than 64%. So it's unlikely the actual parameter value is 0.80, and that gives convincing evidence that the player's claim is not true.
Miss Jones.
Yes.
Can you go over again why for one of those you use p hat and then for the other statistic you just use p?
So when we're talking about our hypotheses, this is the overall population, okay? So he says, no matter what, in the long run, population parameter is going to be 80%. All of these dots are samples. So it's 50 free throws, then he takes 50 more free throws, then he takes 50 more free throws. So each sample is p hat. Each sample is p hat.
Okay, thank you.
You're welcome. All right. I think this is the last one. Where did I stop? All right, be sure that you understand. So I lied to you. We have a couple more. I'm gonna get done. I promise. Be sure that you understand why this evidence is convincing. There are 2 possible explanations. Of the fact that one virtual player made only p hats equal to 32 out of 50, or 60%, 64% of his free throws. So here are the 2 possible explanations. The null hypothesis is correct, that it was 80%. And just by chance, a very unlikely outcome occurred. Or the alternative hypothesis is correct. The population proportion is less than 80%. So the sample results is not an unlikely outcome. Explanation 1 might be correct. The result of our random sample of 50 shots could be due to chance alone. But the probability that such a result would occur by chance is so small, less than 1 in 100, that we are quite confident that explanation 2 is right. Statistical tests use an elaborate vocabulary, but the basic idea is an outcome that would rarely happen if the null hypothesis were true, is good evidence that the null hypothesis is not true. So this last little section is what we're going to do. And I have to do an example because your homework has this. So just bear with me. The idea of stating a null hypothesis, that we want to find evidence against seems odd at first. It may help to think of a criminal trial. The defendant is innocent until proven guilty. That is, the null hypothesis is innocence and the prosecution must try to provide evidence, convincing evidence against this hypothesis in favor of the alternative of guilt. That's exactly how statistical tests work. Although in statistics, we deal with evidence provided by data. And use a probability to say how strong the evidence is. The null hypothesis, H sub O, states the claim that we are seeking evidence against. The probability that measures the strength of the evidence against the alternative, or H sub A. I'm sorry, in favor of H sub O, in favor of H sub A, is called a p-value. All right, so all you need to know for homework tonight, we're going to finish this up, but all you need to know for homework tonight, the first thing is how to write your hypotheses. Okay, so what we did on the check your understanding, and then how to interpret a p-value, and these are really simple. Okay, so the probability, computing assuming H sub O is true, that the statistic, such as p hat or x bar, would take a value as extreme or more extreme than the one actually observed in the direction specified by H sub A, is called the p-value of the test. That's complicated. It's easier than that. Here's what you do need to know though. Small p-values are evidence against the null because they say that the observed result is unlikely to occur when H sub O is true. Large p-values fail to give convincing evidence against H sub O and in favor of the alternative H sub A, because they say that the observed result is likely to occur by chance alone when H sub O is true. Give me a chance to give you an example. All right. So we'll show you how to calculate p-values later, but from now on, let's focus on interpreting them. So the p-value is the probability of getting a sample result at least as extreme as the one we did if H sub O were true. Because the alternative hypothesis was that it was less than 80, the sample results that count as at least as extreme are those with p hat less than or equal to 0.64. In other words, the p-value is the conditional probability so the probability that p hat is less than or equal to 0.64 given that the probability is 80. Earlier, we used a simulation to estimate this probability. As 3 out of 400, 4.0075. So if H sub O is true, and the player makes 80%, of his free throws in the long run, there's about a 0.0075 probability that the player would make 32 or fewer by chance alone. Okay. Again, that doesn't say much yet, but we'll get there. The small probability gives strong evidence against H sub O and in favor of the alternative, which we said that P was less than 0.80, because it would be so unlikely for this result to occur just by chance if H sub O were true. The alternative hypothesis sets the direction that counts as evidence against H sub O. In the previous example, only values of p hat that were much less than The 80% counts as evidence. Against the null. Because the alternative is one-sided on the low side. If the alternative is two-sided, both directions count. So one example and then we'll be done. I'm sorry, y'all. We were supposed to go all the way to type 1 and 2 errors, so I tried to even it out a little bit. I wasn't very good at that. All right, so interpreting the p-value. This is what you need to know for your homework. Calcium is a vital nutrient for healthy bones and teeth. The National Institutes of Health recommended a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers aren't getting enough calcium. Is this true? Researchers want to perform a test of, what is our hypothesis? First of all, do we have a mean or proportion? We don't see any percents, right? So it's got to be a mean. What should they get? 1,300. Yeah, you're good. The alternative. Now they give you this. I'm just getting you to understand how to pull it out. They said they're concerned that they're not getting enough. So what does that mean? Less than. Perfect. Now, again, they give you that. I just want you to be able to pull it out. Where P is the true mean daily calcium intake. Sorry, not P, mu. They ask a random sample of 20 teens. This is the whole problem. I just left blanks in there so you didn't do it ahead of me. To record their food and drink consumption for one day. The researchers should say then. Compute the calcium intake for each student. Data analysis reveals that X bar equals 1198. And the standard deviation of X bar is 411. After checking that conditions were met, researchers performed a significance test. You guys don't know how to do that yet. And obtained a p-value of 0.1404. So your p-value is that probability that they were talking about the last time where it had like the 0.0075 or whatever. It's the probability that it actually happens. So the first one says, explain what it would mean for the null hypothesis to be true in this setting. So what it would mean if it's true. What does it mean? So what does that mean in context of the problem? If H sub O is true, teenagers get enough calcium per day. Interpret the p-value. So this is the one that you need to do. Okay? Interpret the p-value. Assuming that the mean daily calcium intake is 1,300. Okay, so that's going to change because that's in context of the problem. There is a 0.1404. Will change because that's based on this problem. Probability of getting a sample mean. That will only change if you're dealing with proportions. Everybody understand that? So that's just based on whether you're doing means or proportions. Of 1198 milligrams. Again, part of the problem that was up here in the problem. Or less, just by chance. In a random sample of 20 teams. So just watch those. Be careful on this because if it's greater than, you're probably going to put greater than. Okay, so just watch that or not equal to. Got it? And we'll talk about those tomorrow. Okay, I'm going to stop sharing, stop recording.